Hello, everyone, and welcome to the last day of gas laws. So today we're going to be looking at a unique feature of gas law equations. So previously, we built up the van der Waals equation of state, which gives us a fairly robust description of real gases, but unfortunately requires us to use different parameters for different gases. And we have to determine these parameters experimentally. So one of the questions is, might there be an easier way to analyze our systems? Well, it turns out that one way to try and put all of our systems on an even footing is to make use of something called reduced variables. So this is one way where we can try and refer to all of our pressures, volumes, and temperatures for any gas with respect to a common reference points for all gases. So what we're looking for is a common temperature, pressure, and volume that, that all gases will have in common. So this gives us one of two key reference points we can make use of. One is called the triple point, which we'll refer back to later in when analyzing states of matter. And the second is that critical point that we brought up earlier. So one of our best common points of reference is going to be this critical point, because every single substance has a critical point at which we go from a gas or liquid to a supercritical fluid. So you can think of it as the point at which these three materials kind of all coexist, which means that it will have a single pressure, volume, and temperature. So what we can do is try and take our variables, so our pressure, volume, and temperature, and divide them by their respective critical conditions: critical pressure, critical volume, and critical temperature. And this produces our reduced variables. So for example, our reduced pressure can be given as the pressure of the system, so the pressure that we measure, divided by the critical pressure. And the same thing for volume and temperature. And it turns out that if something is reported in the reduced form, simply by looking up the critical points, you can get your system back in terms of pressure, volume, and temperature. Now, one of the things that's really cool about reduced variables is they actually end up being a fairly good way of describing the ideality of a system. So for example, what we can do is graph the compression factor for any gas versus its reduced pressure. So we have an example plot for nitrogen, methane, propane, and ethene. And it turns out that if I have the system at a reduced temperature of 1, so the temperature is at the critical temperature, we get a single plot for all four gases. And a similar thing happens at a reduced temperature of 1.2 and 2. So this actually has some really cool implications. What this means is that, while every gas may have a slightly different van der Waals equation in pressure, volume, temperature space, this means that every single gas has the exact same van der Waals equation in reduced pressure, reduced temperature, and reduced volume space. So this is one possible way of removing our coefficients from our equations of state. And so one of the things we can do is look back at the equations of state we've talked about so far from this reduced variable notation. So for example, let's look at our 5 most common equations of state: the ideal gas, the van der Waals, the Berthelot, and the de Trici. And of course, our good old friend, the virial. So what we can do is replace our pressure with our reduced pressure, our volume with our reduced volume, and our temperature with our reduced temperature. And it turns out that when we do this, what we find is that for the van der Waals, the Berthelot, and the de Trici equation, we end up removing our empirical parameters, which is a really powerful feature. So that, again, showing that every single real gas can be will follow these exact same equations as long as we work in a reduced space. However, what's worth noting is the perfect gas and the virial gas, because of their more fitted form, they're designed to work in pressure, volume, temperature space and not in the reduced form. So these two do not make the conversion quite so well. But one of the other cool things is that what we found is that each of these three forms of the gas equations of state have a certain set of parameters, for example, A and B. Well, it turns out that these A and B parameters can actually be determined from the critical constants. So, for example, we find that the critical pressure is going to be related to the strength of the IMFs and the size of a gas, which again makes sense. However, the critical volume has no dependence upon the strength of the IMFs and just depends on the size of the gas. However, for the critical temperature, again, we see a dependence upon both strength of IMFs and size. So this actually gives us a lot of information about A, how we can determine our critical conditions, but B, also how the behavior of our gases will tell us at what point we move from an ideal system to an ideal gas to a supercritical one. And this is actually a fairly useful metric. So if it turns out that you can't find your A and B parameters for a van der Waals equation, you can always look up the supercritical point and try and convert. So with this fun little detour, this brings us to the end of our gas laws. So now that we have a good set of equations of state in hand, that we can go ahead and describe a gaseous system, next time we're going to start our long journey for describing the energy and behavior of a system, continuing with gases. Till then, take care.